Okay, so this is like the corner algorithm. As I said, it's I think the most complex algorithm in the whole course. So the first step is you compute M matrix. Okay, M matrix, you know, like what are the components, you know how like all these steps are being computed. And once you have that, then you try to compute cornerness score for each pixel location. Okay. Then a lot of heuristics involved. First of all, like how to compute cornerness. Again, we have some heuristics for that. And it's not just heuristics, like there's a lot of theoretical backing to it, again, which we will not be able to cover. And then we put like some kind of threshold on this cornerness score to determine whether that point is corner or not. Okay, so once we have done that, we will perform non-maximum suppression. You have done that earlier for edges as well. So it's exactly the same algorithm. And the idea is like, if you are saying this particular location is a corner, then you should make sure that there are no other corners in the vicinity, right? You should have like some very unique corner. And that's the whole idea about using non-maximum suppression here. And the idea of threshold is just when you don't want to detect too many corners. So that's why you need to set some kind of threshold. And the intuition is same, like which you used for edge detection. You have some sort of threshold there, right? To determine like whether this is an edge or not. Okay, so let's quickly go through each of those steps. And this is your input image. You can compute like these partial derivatives, Ix, Iy, and you can perform blurring as well. You know that if you perform some kind of blurring or smoothing using Gaussian filter, that improves your edge detection. So that's optional, but you can do it. You can compute like the components for M. This is just Ix square, Iy square. So this is, you're just multiplying the element wise these values of the matrices. Okay. And then you have like Gaussian filtering on top of this. This is one additional step. And then you have a equation for cornerness. And again, don't ask me like how you get this. Again, there's a long theoretical proof for this. And this also involves like eigenvectors, eigenvalues, which we briefly covered in the second lecture, right? But I think we really don't have time to talk about all that. But you have a function which actually tells you which of these points are actually corner and which are not, which will give you some kind of score, which looks like this. And the equation is exactly like this. You compute the determinant of this M matrix, the image moment, and you compute the trace, and you have some, again, one alpha parameter here. Okay. Then, as I said, you use a threshold to pick like which is corner, and then you perform non-max suppression to identify which are the peak values or which are the corners. Okay, so again, this is one of the first corner detection algorithm, or you can say key point detection algorithm. So I just wanted to talk about this because this is like gives you an idea like how it all started and how complex it was. And let's look at like some of the results. Okay, so these are the input images. You can see the lighting conditions are different. It's slightly rotated as well. This is computing the cornerness response. So after you compute the M matrix, you have that equation where you computed the determinant of M, then the trace of M, and using the parameter alpha, you get this response. Now you see that you are detecting a lot of corners, right? This is not really useful, and therefore you need a threshold. Okay, so you set a threshold and you say that, okay, only some of these are corners. And then you can see that, okay, this really needs some kind of non-maximum suppression, because in this vicinity, you can't have like all these key points. And you run that algorithm where you suppress like the neighborhood, only pick like which has the highest intensity. That will give you these key points. And you can see that the images were of the same object, right? And the lighting condition was different. The right image was slightly tilted, slightly rotated. But if you carefully look at like the key points which have been detected, I mean, they kind of match. Okay, and that's why like these key points are very powerful. These key points like plotted on the image itself. You can see, I mean, you don't have any key point on the flat surfaces, right? Only at these interesting points, which is pretty cool. You can see like this interesting shape here. You have a lot of key points on this boundary. So in a way, if you think about this, this is kind of trying to find the boundaries. Okay, so that's one use case. You can see like it's on the boundaries, right? And again, not like very flat boundaries. You can see like if, for example, these feet over here, right? It's you don't have any key points here. So if it's kind of curvature, or if like you have different edges meeting together, those kind of points you can see on the horns here, right? So those key points are actually detected. Okay, I know like that's a lot of maths there, and as I said earlier, I don't expect you to understand all of that, but at least if you can understand like these steps, how this algorithm is actually extracting key points, I expect you to understand that how you compute gradients, you know that how you're getting these matrices, this like just you use those equations, right? And I don't want you to understand like how we derive this equation. As I said, it was decades of research, which will be very difficult to cover like in just one lecture, even in this course.